Hi everybody, I'm Dermot O'Shea. I'm the host of the Antenna podcast, and today I'm delighted to be with Lars Jakob Foged. Is that right?
It's pretty close.
Tell us how you say it properly.
Lars Jakob Foged.
Full. Okay, Lars, do you want to introduce yourself? Tell us who you're with and why you're here at the EUCAP.
That would be nice, yes. I'm the VP, so Vice President of Microwave Vision Group. I'm responsible for research and development. And we've actually been part of EUCAP for 20 years.
Okay.
And I've been going to all of them except for one, which I was terribly ill and therefore couldn't go to. Otherwise, I've been to all of them.
Okay.
So this will be my 19th in the 20th year of EUCAP.
Wow. So, and EUCAP is the European Conference on Antennas and Propagation, right? And MVG, do you want to tell us how you guys come into play in our antenna industry?
So a very important part of what is going on here at EUCAP is really related also to measurements, because in the end it is the antenna propagation, but the antenna part also requires some kind of verification. And it is clear that a lot of the activities going on in EUCAP is basically about how to make better antennas, antenna theory and so on, but there's also a very strong component that is linked to how you measure and how you determine performance of these antennas. And as a company that is a leader in the industry of antenna measurement systems, we always felt from the beginning that this was a place we had to be.
Gotcha. And so tell us maybe a little bit more about yourself, what your career to date has been and how you got into this area.
So that's a good question, because I need to think if I can remember that far back.
Okay.
So the point is that I started out, so I am Danish in origin, and that's why my name is a little bit difficult to pronounce. I actually went to school in engineering school that was more for, let's say, applications, so more like for people who had been in the industry for a while and who wanted to become an engineer. So after I graduated there, I wanted to go out and see the world. And I actually went to US for a few years to California Institute of Technology.
Okay.
And I was there for a few years. And after that, I came to the European Space Agency.
Okay.
As a young graduate internship, which is a fantastic way for young people to get an introduction to the world of satellites, and in my case, for antennas for satellites.
So what did you study in California Institute that would have got you that internship? Because this is a question we always ask at the end. We'll ask it now. What advice do you have for people that would be interested to get into our industry? So
the interesting part is that what I studied in Denmark had really nothing to do with, in the end, what I started to study in the US. And my interest in US was electromagnetics, but definitely not, let's say, in antennas. It was more microwaves. But when I came to the European Space Agency, let's say the possibilities or whatever was more in the antenna area. And therefore I started to work on antennas when I was in the Space Agency.
Okay.
And after that, I have to say that I started really to pursue this idea about the antennas. So I looked for another possibility to not go back to Denmark, but I wanted originally to go back to Denmark. So I went to Italy, again thinking that maybe it could be a few years and then I could go back to civilization, as I said at the time. Now I know better, but no offense to the Italians, and then they know that I love them, so it's okay. So the idea was really to have a short period of, let's say, of good experiences in Italy. But I ended up staying, and I've been living in Italy for more than 30 years now.
Okay. Whereabouts in Italy are we talking?
The Rome area,
okay.
So central part of Italy. And so in the beginning, I started working in antennas for space. I worked about 10 years in that industry.
And in ESA?
So that was a company that was sort of working for ESA at that point. So I had to leave ESA after the internship that I did in it. And then I went to the industry, working more like a consultant for antenna designs for satellites.
Okay. So you were doing the design of the antennas as well?
We worked very close with what was then called Linea Spazio. One of the things that we designed that was interesting is one of the satellites that were used at the time for satellite broadcasts over Europe, the EUCAP. So you've probably seen some of the football matches on the satellite network, and probably that antenna was designed by us at that time.
Okay.
So I got involved.
What frequency was that for?
So that was in the KU and KA band.
Okay.
At the
and
time.
What kind of antennas were there were?
These were very interesting reflector antennas that to get a good separation between the two orthogonal polarizations, the first one was gridded. So it was actually a wire grid, and then the back one was a solid reflector.
Okay.
And so we had to let's say, make a few advancements in technology in order to get that done at the time. Also in the part of simulation. We're talking about more than 25 years ago, so the simulation software were really not that evolved as they are today.
Very slow, yeah.
Yeah. So we had to use, let's say, physical optics because it was the only thing that could handle reflectors of that size, and we had to do a little bit of tweaking using other codes to calculate the penetration of the first grid area into the more solid area that we can then treat also with the physical optics to take into account the fact that there were two real reflectors and they were sort of interleaved so that they could work. One could work in one polarization and the other would be working in the other polarization.
So they were dual polarized.
Yes,
yeah.
dual gridded.
And dual gridded. And what was the main challenge technically? Was it distance? Was it gain? What was your main design parameter?
So what was also interesting about this is that we at that time what they call the shaped reflectors were very used. So by shaping the surface slightly deviating from a parabolic surface, you can actually introduce a sort of a phase tapering of the surface and shape it so that the energy only goes to the area in which you're really interested. Okay. So if you look at Europe from space, for instance, it is a blob, but the contours are pretty significant. You don't want all your energy to go into the sea or elsewhere. You want it to go to the actual, let's say, customers that are willing to pay for your services. Yeah. Okay. And so the design was really intriguing in the sense that we needed to make our own software at the time to actually do the shaping of these reflectors. To make sure that they had a good performance in the areas of interest to the customer, which was EUCAP at the time. So they gave us a contoured, let's say, part of Europe that they wanted to cover, and we needed to squeeze as much energy we could from the reflector in there. Okay. So it was very challenging, very interesting. Not only that, but for one of the first times, I think, in the industry, we were challenged by the fact that in space, when the sun sort of falls onto the reflectors, they don't fall on the reflectors all in once, but they actually do sort of like gradient type move because there's a shadow from the satellite as well. And so we had to compensate at that time for what we call the thermal distortions of the reflector. So we had some mechanical people in Linea Spazio calculate what kind of thermal distortions could we expect from the ideal shape of the reflector. And we also put that into our calculations as well and tried to find a profile that would be resilient to this kind of distortions of the actual surface. These are all things that we do today commonly in software, but 25 years ago, 30 years ago, it was a bit of a challenge to do. Considering
and you couldn't look it up on the internet or ChatGPT.
It was difficult. There. It was difficult, and so it was a very, very exciting moment for a relatively young person at the time to work on what I think was the forefront of technology at that time, really. So I was lucky to get to the point where we actually manufactured these antennas and delivered them, and they were also tested. And in the end, it turned out that our predictions were correct, that they actually worked.
Awesome.
So it was a very nice experience.
And what about now, obviously, as you know, there's satellites launching every day.
Oh yes.
And there's antennas all over them, and what we've found is the environment your antenna needs to live in is extremely challenging in space, right?
Yes.
And you guys back then, how did you get around that challenge? Because that's another, the technical challenge is one piece, but the mechanical engineering challenge is almost as difficult.
Yes. So one of the things that I like to tell people in our company is that I have assisted in many discussions between mechanical people responsible, of course, for important things, not only on satellite design, but of course it's maybe the most intriguing, and people responsible for the electrical design. Because the electrical engineer would say, well, I mean, take the reflector, just hang the reflector there, and you don't have to put 10 kilos of support structure, because you just need to put a few screws. And the mechanic guy would go say, no, but I mean, here we have to be sure that it doesn't bend, it doesn't destroy itself, or so on. So the discussions could be pretty heated between these two people who are in disagreement on how to do certain things in terms of accommodation. But today, what we're seeing is that, of course, cluttering a satellite with lots of antennas because you want to have let's say many services integrated on the same platform, creates another problem, which is that of coexistence. So the fact that having one antenna operating at some frequency, working in the same environment as another antenna working on another frequency, is going to have an impact on both performance.
Interfere with each other.
Yeah.
Yeah.
And one of the things that I took with me, because after I worked for a while in the space industry, I also that's when I came to the microwave vision group, which was in 2001.
Okay.
So we haven't gone very far in my career, actually. Now we are 25 years ago, basically. And I wanted to join the microwave vision group at the time because it was a very innovative, very small company at the time. Today we are almost 500 people, but at the time we were 15.
Wow.
So one of the things that they studied, and I was very intrigued about, was the possibility of representing an antenna from measurements. So by measuring an antenna, trying to derive a mathematical expression for that antenna, so you could use it in your simulations. And that has a lot of value because it's a way that you can actually measure these various antennas, put them into your simulation environment, and then understand how are they going to interact from the calculations, and then you can maybe get some better ideas about how they should be placed also, for instance, on a satellite or on an automobile or any other large platform in which you have the need to have many antennas, but you don't really have, let's say, the room for them. You have to sort of find the optimal positions. And we started slowly working in the beginning on that. And over the years, it's one of the things that we have developed that I'm pretty proud of, is this particular tool using and expensing using equivalent currents.
Okay.
So what we can do is that we can measure an antenna pattern, and it can also be an active antenna like a mobile phone. From that, we can actually project the equivalent currents, electrical and magnetical, onto the surface, a surface conformal to that particular antenna that you're trying to measure. So a mobile phone, it will be the upper surface. For a horn antenna, it will be the outer part of that antenna. And
so the surface of when you mention surface, you mean it's the actual outside surface of the phone.
Exactly.
Or the outside surface of the horn antenna.
Exactly.
Okay.
So a surface that is conformal, so it doesn't have to have any information about what is inside. And those currents will represent fully the radiation of that antenna. And what the beauty of that is that those currents are compatible with most of the computational and electromagnetic tools we have in industry. So not only the one from MBG, but from everybody in this industry can actually use those currents in their calculations. So now we have a scenario that I couldn't have 30 years ago when we were trying to do this in the space industry, where you can take the antenna that somebody else is making, it's already existing, you measure it, and then you have a very accurate, fully EM model of that antenna, and you can use it to find the best position onto your platform for making sure that it works in the best way, of course, and making sure you get room for all the antennas working on the platform.
That's fantastic, yeah, because I know with theory and simulation are one thing, but actual real-life performance brings up unexpected results,
Very
right?
very often, yes. So, for instance, the material, even though we've done a lot of progress, I mean, back in those days, FR4 was a material we used for some of the antennas, but it could vary a lot. Now, of course, they are better, but very often we see that also because we are squeezing the performance of the antennas, we're really, with the tools we have, we are very reliant on the fact that the materials have to be the ones that we think we're using in our simulations. And therefore, often small deviations will make the antenna performance not be exactly as our numerical model. And that's where a real measurement of that performance is valuable.
And you guys came up with this technique and technology. This is your
Yes.
invention.
We will call it that in the sense that it was a collaboration between Microwave Vision Group and University of Turin, the Polytechnic of Turin. And it was actually started as a small project with the European Space Agency.
Okay.
So we had this desire to go in that direction. They had at the time the knowledge in Turin to make the let's say the engine for doing the computation using the equivalent currents, and so we started this partnership, and it has actually been running for basically 15 years now. In which we have developed a tool that can do this. It's an integral part of our measurement systems.
Okay.
So if a customer buy one of our systems and they would like to generate these kind of models for their use, then they have access also to this as a post-processing tool on the measurements.
And so yeah, so it's good to know, because for me, MVG as a company, I know what was previously called Satamo
Exactly.
is now MVG, and what we love it for is the speed that we can do our antenna measurements
Yes.
in, and our OTA measurements that used to take 2 hours to do, maybe TRP or TIS or something like that. Now we can do it in 10 minutes.
Yes.
But you're much more than that. So you're the VP of R&D, you said.
Yes.
Is it all antenna R&D, or obviously what other areas of measurement are you guys involved in?
So it's a lot more than just let's say antennas.
Yeah.
Even though I sort of started in that area.
Oh no, well yeah.
And it's really all the aspects about antenna measurements. Both we divide that world in passive and active. So when you mentioned the OTA measurements, the fact that you would like to have TRP measurements or sensitivity, also that part is part of the R&D that we do, trying to develop new methods that will allow us to do this faster and more accurately. And also in, let's say, what we call the passive and measurement range, that is now, for instance, including RCS, which is very up and coming, let's say, problematic for the defense industry.
So what's maybe explain that to the guests? It's
so
RCS.
So the radar cross section of an object is, let's say, it's important to know because it's part of developing, for instance, aircraft with stealth capabilities. There you need to reduce what we call the radar signature. So how much energy is actually being reflected off the object, in aircraft in one case or whatever. So
you can't detect, you don't want it to be undetectable, is that the point?
Exactly. And what is interesting though is there could also be an opposite on this, because for safety, for some of the radars in our cars, we may actually go the other way around and would like to put targets maybe on the cars to make sure that they are more visible, because in a, let's say, a civil application, it's nice to know where things are. So, so it's not only to let's say make it less. It could also make sure that you can actually be seen.
Yeah, we're in Dublin here for EUCAP, and the best way to get around is on the city bike rentals. And I wish the Dublin buses knew where I was. That's all I can
Yes.
tell you after
Also
using the
because-
bicycle to get around here.
Yeah, for me, for instance, that I'm not used to driving in the wrong part of the road. Probably other people will tell me I am on the wrong path, and that is another stress factor, because you need to know, and then be careful in traffic. So clearly there are also civil applications for radar cross section, and again, it's something we are developing in MVG as well.
Okay, excellent. And then so maybe in a question we like to ask here on the Antenna podcast is like, what use case or application are you most proud of, or did you find most interesting or challenging? You may have already told us with the satellite antenna.
I think so we sort of touched upon, I think, the two major things that I'm the most proud of, but I have to be honest, maybe it's more on the personal side. I think a lot of young people have joined MVG or SATIMO at the time, and has been through, let's say our model for creating people, for creating engineers, and some of them have then later moved on into other areas. And I think we have been very lucky to touch upon quite a lot of a set of brilliant people that even though they have not remained in the company, they went off to do very important things also, which I'm very proud of the fact that we were able also not only to, let's say, develop new products, to innovate and try to be on the forefront of everything, but we also had a very nice human area, a human face of our company, and we're able to attract nice people that we're still friends. They're doing great things out there, and of course all the nice people we have in the company as well. That's I think one of the things that I think is important. Working in MVG is nice because people try to work together and help each other in a very good way. And this is maybe one of the strengths that we have as a company. And I'm proud that I think that I gave a little bit of a small piece of that. I think is also my doing.
That's a great answer. And you have nice international spread as well, which is always enjoyable working in a company that has an international footprint. And
it's a let's say it does require, for instance, that you are a little bit more patient because you're working with people that have different backgrounds. Sometimes we have linguistic problems, so which is possible. I mean, it
guys
happens.
with Irish accents and stuff like that.
Exactly, and which is not always so easy to understand each other. But that also means that people try to be a little bit more open, and it's good. It's a good environment to be exposed to, just because of the fact that you are so international and really in a learning environment. I
love that, yeah. And then you can forgive each other for bad football results before European Championship playoffs.
Or you can insult them the day after, maybe.
Denmark
yes.
is a sore point in Ireland. Anyway,
that is true. That is true. Yes.
So
even Italy is a sore point, by the way.
Well, three World Cups in a row. That's really painful for Italy not to be there. It's unthinkable. So. Yeah, we like to do a quick deep dive into a technical topic as well. Yeah. Maybe you could. We've mentioned many terms there already, but maybe you could give us something that maybe listeners could find interesting and useful.
So, one thing we could briefly discuss upon is what I would like to call an emerging technology in antenna measurements. That we also have presented here at EUCAP. The idea is that for doing antenna measurements, we generally would like to be in the far field. It's a little bit strange because most of the communication that is done is actually in near field, or at least finite field. But it's very convenient for all of us that if you test an antenna and you want to compare it to my test, it has to be in the same reference condition, so we use the far field. Okay. So we are really striving to find good methods to measure easily antennas in far field. And for a long time we've been considering, for instance, the compact antenna test range as a reference for creating far field conditions in a test environment like a smaller chamber. But recently we started to study the possibility to use plane wave generators based on an array of feeds. So we are right now studying the possibility to build very compact measurement systems that is based on an array of feeds that if you amplitude and phase them correctly, they are going to approximate a far-field condition very, very close to the surface of the actual array, making the antenna measurement system very compact and very versatile, because in the end, even the array can be movable if you design them correctly. So you're no longer, let's say, restricted to have an anechoic chamber in which your large reflector is fixed in the room and aligned very well with your feed. But you can, in some cases, even take your plane wave generator and move it in case you want to interrogate something in the far field. And the measurements that you do are transformed directly from the near field that let's say, are coming into on the array surface, goes through the array processing essentially and comes out as a far field signal on the other side.
So it's like far field measurements in near field conditions.
Exactly.
Okay.
And this, I think, is a very promising technology. I see also other people are starting to work in this area. And I think this is rather intriguing and maybe also a logical, let's say, consequence of the fact that many of the communications we are going to have in the future are going to be based on large arrays. So everything is getting smaller in terms of elements, more integrated. People put elements together, try to have them work as, let's say, as one, creating phased array type applications. And therefore, let's say, the corresponding technology in measurement would be to do more or less the same, to take advantage of these advancements in antenna design for arrays, for the beamforming technology and so on, to actually make these systems that can not only approximate a plane wave condition, but in the end, and that's where we need to go, we're not there yet, even approximate real-life conditions. So when you are testing, of course you would like to know the far-field response, but once you know that one, then you probably would like to see what happens when I take this device or whatever out in the real world. And having the possibility to test that directly in a compact environment using, for instance, a plane wave generator, asking the plane wave generator not to make a plane wave, but to make a complex wave that really looks like the scenario where your antenna is going to be working, or your device is going to be working in the end, is something that we need to resolve. So it's not ready yet.
Yeah.
But it's something that we would like to do.
That sounds, it sounds exciting, and that's going to be a great solution for our industry. Like, that's why, I suppose that's how we in Hourglass exist, because people get very unexpected results when they actually install an antenna and go to real life rather than what they actually got from the lab. So having the ability to more accurately measure and simulate real life environment in the lab is so useful.
Yes.
So
that's a step that we are sort of scratching the surface now, but it's something that I think we need to see in the coming years.
Great.
Some more developments.
Yeah, really interesting area, and something we definitely want to cover more in the future of the Antenna podcast is the area of measurements. So where's the best place for people to find out more about this, Lars?
So we've done quite a few publications.
Okay.
So even in this conference, we have published quite a few results. So the literature is maybe the best place to start. It's also been mentioned in some of the standards. Okay. So some of the antenna standards from the IEEE, we are already reporting a little bit on how to do the plane wave part of this. So that's a good place to start. And another good place could be to come and talk with me. Yeah. And I will be willing to explain more or less what I know and get people started in this area if they want to do more.
Fantastic. Well, listen, thanks very much for your time today. It's been a great discussion. I'm Dermot O'Shea, the host of the Antenna podcast, and Lars, thanks very much for your time.
Thank you. It was great being here.